Okay, let's jump right in.
Let's do it.
We're doing a deep dive today into some really practical technical stuff, foundational for modern AI infrastructure.
Absolutely critical stuff.
And our source material for this, it's actually pulled straight from excerpts of the NCP-AIO exam practice questions and solutions.
Yeah, and it might sound like just test prep material, but what's interesting is how these questions and the answers, they really distill complex, actual real-world challenges.
Hmm.
And crucially, the most effective solutions for AI deployments. It's almost like a shortcut,
Yeah.
getting straight to the key pain points.
Exactly. Think of it like getting the cheat sheet on some vital AI infrastructure knowledge.
Yeah.
You avoid digging through like mountains of docs. We're going to pull out the most important bits, those aha moments hiding there, and help you get up to speed quickly on these essentials.
Yeah, our mission here is really to unpack these specific scenarios the source brings up, understand why the recommended solutions are the right ones.
The why is key.
It is, and see how all these pieces fit into the bigger picture of building and managing these high-performance AI systems.
All right, let's get into it. We'll start with something loads of people hit early on.
Okay.
Imagine you're trying to deploy an AI workload, maybe using a container from the NVIDIA GPU cloud catalog.
Right, standard practice.
You just drop it on your system, but bam, it hits a wall. Why? Because the NVIDIA driver on your host system, it doesn't match the one the container expects or was built with. Why is that mismatch such a fundamental issue based on the material?
Well, this goes right to a really core compatibility requirement.
Yeah.
The material is very clear on this.
Okay.
The NVIDIA driver installed on your host OS, it has to be compatible with the CUDA version that's actually inside the container. CUDA being NVIDIA's platform for talking to the GPU.
So if they're not compatible, it's like they're speaking different dialects, or worse.
Probably worse. It's more like trying to plug some really advanced piece of kit into an old, incompatible socket. The source explains the recommended way, and it's simple but vital. You've got to match the container's CUDA needs with a compatible host driver. If you don't,
Your GPU just sits there.
pretty much,
Yeah.
it likely won't function correctly inside that container.
And I like that the source spells out why this is the best way. It helps you skip the messy workarounds, doesn't it?
Exactly right. The material points out that matching ensures the GPU works like it should, and importantly, you sidestep having to, say, rebuild the whole container image with different bits.
Which is a nightmare.
A total hassle. Or even worse, like disabling the CUDA version checks in the runtime. That can lead to really unstable or unpredictable results.
Got it. Okay, so for you, the listener, this first takeaway is, well, it's gold. Check that host driver and container CUDA compatibility first. It'll save you a world of trouble later.
Absolutely. Now, okay, once you actually have your workloads running, especially if you're dealing with lots of GPUs.
It's like in a big cluster.
Exactly. Across multiple machines, a multi-node cluster. Keeping track of their health. That becomes a whole other challenge. You need eyes on things like temperature, utilization, error rates.
Sounds like monitoring the vital signs for, I don't know, hundreds of athletes all at once. What specific tool does the source point to for this kind of big-scale GPU checkup?
The material is very specific here. The recommended tool is DCGM.
DCGM.
Data Center GPU Manager.
Okay, DCGM. I mean, there are lots of system monitoring tools out there. Why does the source highlight DCGM for GPU health across clusters? What makes it stand out?
That's the key thing. The explanation really emphasizes that DCGM is specifically built for GPU health metrics.
Ah, purpose-built.
Exactly. It's not just a general system monitor. It's tailored to pull those critical data points, temp, utilization, errors from the GPUs themselves. And crucially, it's designed to collect and manage this across multi-node clusters.
Right.
Trying to do that manually or maybe with less specialized tools on a big AI system, it would be incredibly hard, inefficient. DCGM gives you that central GPU-aware view.
So if you're running distributed training, managing a GPU farm, whatever, DCGM is kind of your essential dashboard for hardware health and performance.
That's right.
And keeping that hardware healthy, well, that's just table stakes for reliable, efficient AI training ground.
It really is, yeah. Now, shifting gears a little bit, the source is also getting some specialized hardware components.
Yeah.
Things designed to really boost system efficiency.
Okay.
They mentioned Bluefield DPUs, data processing units.
GPUs.
What's the main benefit, the main role of a DPU in AI infrastructure, according to this material?
Yeah, DPUs are still a bit newer for many folks compared to CPUs and GPUs. What's their main job? What does the source say they really bring to the party?
So the core benefit that's highlighted is offloading. specifically offloading data plane processing tasks from the host CPU.
Offloading, so like taking work away from the main CPU so it can focus on the actual AI number crunching.
Precisely. The material explains that things like networking functions, storage operations, even some security processing,
Yeah.
data plane stuff.
The busy work of moving data around.
Kinda, yeah. That gets moved onto the DPU. You can think of the DPU as this really powerful, programmable combination of a network card and storage controller, plus more. By handling those tasks, the DPU frees up the host CPU's cycles. The CPU isn't constantly getting interrupted managing data traffic. It can just focus its power on the complex AI compute.
Okay, I think I get it. So instead of the CPU being the main brain and the traffic cop for all the data,
Yeah.
the DPU takes over as the specialized traffic cop. So for you, the listener, this means more of your expensive CPU power is actually doing AI work, better efficiency.
That's a really good analogy. And speaking of moving data,
Yeah.
let's hit a major bottleneck in the material highlights. I/O latency.
Yes. The class.
Getting data from storage to the GPUs fast enough, it can absolutely kill your training speed.
Yeah, it's a huge pain point. You've got these super fast, expensive GPUs just waiting for data. What action does the source say is the most effective way to tackle this specific I/O latency issue?
The source is pretty emphatic on this one. The most effective action. Moving to GPU direct storage-enabled NVMe SSDs.
GPU direct storage. Okay, the name alone sounds fast. But why is that solution so much more impactful than, say, other tweaks you could make?
Well, the explanation cuts right to it. GPU direct storage lets data transfer directly from NVMe SSDs.
Those super fast solid-state drives.
Exactly, the ones usually on the high-speed PCIe bus. It lets data go straight from there to the GPU's own memory. And the crucial part, it bypasses the host CPU and the main system memory.
Whoa, okay. So instead of storage Mayo CPU, system RAM, NAS GPU, it's just storage Meso GPU, like a direct highway.
Exactly, a superhighway. By cutting out that CPU and system memory detour, you just slash the latency. Boost the throughput massively. It directly speeds up how fast you can feed those hungry GPUs.
Right.
The source even contrasts this, noting that, software changes like tweaking training parameters, dropout rates, image sizes.
Stuff you might try first.
Yeah, things you might try. They just don't hit that fundamental hardware bottleneck in the data path nearly as effectively as GPU direct storage does.
That really makes it clear. Faster data access means faster training. It's tackling the root cause.
It absolutely is. Okay, finally, let's zoom out a bit. Look at how AI systems can be architected. The source material touches on disaggregated infrastructure design.
Disaggregated.
Okay. What's presented as the main advantage, the key benefit of designing an AI system like this.
Disaggregated infrastructure. Well, it sounds like you're breaking apart the traditional server box, right? Where compute, storage, networking are all bundled tight.
That's the idea.
So what's the big win there, according to the source?
The core benefit stated is flexibility, specifically flexibility through independent scaling.
Okay.
Disaggregation means you separate out your compute nodes, the servers, with the CPUs and GPUs from your storage systems, like big pools of SSDs, and also from the network fabric itself. They become distinct resource pools.
Independent scaling. So you're not forced to buy a whole new, bigger box if you just need more storage, for instance.
Precisely. The material explains that because these resources are broken apart, you can scale each one up or down independently, based on what your workload actually needs right now. So, if your models suddenly need way more storage, but compute is fine, just add storage. Need more inference power for more users, but storage and network are okay, just add compute nodes.
Right.
This flexibility, it improves your overall resource use, your efficiency, compared to those rigid all-in-one systems.
Okay, so it's more like building with Lego bricks instead of those pre-made kits. You can customize and add just what you need where you need it.
That's a great way to put it.
For you, the listener, that could mean much more efficient use of resources, maybe better cost management as your AI needs shift and change.
Exactly. It lets you tailor the infrastructure much more closely to the often unpredictable demands of AI workloads.
Well, that wraps up our deep dive for today. Keep learning, keep exploring these really fascinating parts of AI infrastructure.
Absolutely.
Catch you on the next one.